Hello everyone, my name is Saeed and I'm going to talk about our recent work on face editing using a regression-based approach in the StyleGAN latent space. The goal of face editing is to change an attribute of a face while retaining the unrelated attributes and also the personal identity of the face. For example, I'm showing two examples here when I want to change the hair color from black to blonde, but the one on the left, it also changed the skin tone and identity, but the one on the right, it only changed the hair color. So the one on the right is preferable compared to the one on the left. Okay, now let's talk about our method, the latent-based regression. So the previous research, it shows that it is possible to train a regression model in the latent spaces of StyleGAN. For example, given a latent space, we can predict the face, the attribute. Like for example, we can predict age or yaw in degree. This suggests that if we move in the attribute's linear latent direction, the amount of the corresponding attribute of a given image would change. So let's say given a face, for one particular attribute, we know that the amount of that attribute is y1. If we move in that attribute directions, and we do some math, very simple math here, we can see that if the W's they have a unit norm, we can change the amount of the attribute. So this is very useful. It means that we can visually change the amount of the attribute as well. Okay, so this is the linear regression, how we train that. So we need some data, so we can collect a lot of faces, and then we collect some labels using attribute prediction network or some clip-based approach in the paper, we talk about that. I'm not going to talk about it in this presentation, but please refer to the paper when we use clip to collect some data. So this is for y, the values of the attributes. Also, we need some latent code, and that is also easy. We can get one pre-trained encoder, which in this case we use E4E encoder to get latent space of these several images. And once we have those, finding the directions, the W's are easy. It's just a simple linear regression. So that linear regression may have a lot of solutions, and we only interested in those solutions that when we edit one attribute, the other attributes does not change. But if we don't add any regularization to this linear regression, we may not achieve that goal. So I'm going to show some results later, but the first regularization that comes to our mind is to use weight magnitude. L1 and L2 metrics are commonly used when performing regression in high-dimensional feature space. The primary effect is to reduce the impact of its significant independent variables and prevent overfitting. And we found that both highly improve the quality of the edited images. Now the question is a StyleGAN latent space type important? It can be important. For example, if we are using style space, it is useful to use L1 because we know that the style space of a StyleGAN is sparse. Therefore, the direction should be sparse, and then we can use so we can use L1, which can encourage the sparsity. But for WP plus space, we have seen that like L1 or L2 works quite well, and we don't have any we don't prefer any of them. Okay, so let's talk about the other regularization, and the other regularization can be added to the linear regression is orthogonality. So let's recap to the goal of the face editing. We want to change one attribute, but we don't want to touch any other attribute, right? And that can be done with orthogonal directions. Let's consider two orthogonal attribute directions, W1 and W2. So these are, for example, corresponds to two target attributes. For a given latent face latent called X, we can predict the amount of the attribute 1 and attribute 2 by the simple linear equation. So now let's move in W1 direction and see what is going to happen to Y2, or like the amount of the second attribute. Well, if directions are orthogonal, the amount of the attribute second, it's not going to change. So, and that's all we want, right? And also we can have the similar discussion for Y1 if we move to the directions W2. So that's useful. That's all we want. So it is intuitive to also apply this orthogonality between the directions between all the attributes, right? When solving the linear regression. Okay, then the full objective is the full objective has two regularizations term, weight, magnitude, and orthogonality. We are gonna see the difference between these two, and then how important. Okay, let's look at some results. We use 60K training FFHQ images. We use a pre-trained attribute regressor to collect labels. And also, as I mentioned before, we can use the pre-trained E4E network to inverse an image to the latent space W plus, and then we have the mapping. We have the mapping to get this the style vectors. Okay. Then we can use our full objective to find the attribute directions. And once we have those directions, then we can add those to the original latent code together with some sliders. So these alphas, they control the amount of the edit, right? So if alphas are like high and they are positive, you can change the attribute to the to the positive size, or like you can change it to the negative size, as I'm going to show later in the results. We have a lot of experiments, so I added several of them here. You can go back to the paper if you are interested for more information. One is like attribute manipulation. So we can do a lot of things. We can add hair, we can add a smile, or change yaw. And as you can see, all other attributes stay the same, and we only can target one particular attribute. Identity preservation is also very important, because if you edit the image, if you a lot, right, we don't want to change the identity. And this is the comparison between our method and to the method in the state of the art. And as you can see, even with the very large edit, the amount of the attribute change for our method is it's lower compared to the state of the art. We have another experiments to look at the importance of L1 and L2 regularization. So if the first image, if we don't add any regularization, we don't get any good results. The target here to change yaw, but once we add more regularization, the method starts working. And orthogonality, as I mentioned, it's very important. In this case, we train our model twice, one without orthogonality and one with orthogonality. And as you can see, if we don't use orthogonality, there are some entanglement between making this person younger and also smiling,